All right, this week we'll be going through non-ohmic components. There's a quick circuit review up there for both series and parallel circuits. I'll give you a moment to have a read through that. If that wasn't enough time to read through it, just pause the video and take as much time as you need. Let's move on. All right, so we have non-ohmic components. The first one is a filament lamp. It says, the graph for a filament lamp is not a straight line and therefore does not obey Ohm's law. So remember, if we're sort of looking at either an IV characteristic, here they're plotting current on the y-axis against voltage on the x-axis. So it would be the inverse of the slope here, okay, that would give the resistance. But this is not, here it might sort of appear to resemble Ohm's law, but certainly we can see that that's not a straight line, that as we increase the voltage, the current doesn't keep on rising with it. So like right here, we're increasing the voltage and the current's going up, right along with it. But then it's like, well, for the same sort of change in like 1-2 units of voltage, see how much it goes up? But then here we have the same 1-2 units of voltage and it doesn't go up hardly as much, right? So that's the evidence of this is some non-ohmic component that is not obeying Ohm's law. We don't get it as a straight line that goes forever, right? They give an explanation here in this little box as to why that's the case. As more current flows in the lamp, the metal filament gets hotter. The metal atoms in the filament vibrate faster and further from their positions. This results in an increase in collision with the traveling electrons, hindering their flow and causing more resistance. This is shown by the flattening out of the graph as the current increases, indicating that the resistance is increasing, right? So remember that, like, if we were to take the slope of this part of it, it would be close to zero, right? Like very flat, very shallow slope. The inverse of a really, really low number is a really, really high number, right? And so that's evidence of, oh, whenever the curve sort of starts to flatten out, that's like when it's got really, really high resistance or it's approaching infinite resistance on an IV characteristic, right? Because it's sort of tricky because you have to remember, okay, the slope is zero, but the inverse of that would be like close to infinity. So a filament lamp. There are things called negative temperature coefficient thermistors. A thermistor is a thermal resistor, okay? And so you can kind of see like this is what it's a plot of resistance against temperature. And so it's really dependent upon temperature. For this one, for an NTC, as the temperature increases, right, so we're going up in temperature, look what happens to the resistance of it. It goes down, decrease. So it becomes less resistance with higher temperature. Usually that's because this thermistor is made of some kind of a semiconductor, a metalloid that doesn't usually conduct, but if you give it some energy, like heat energy, you free up more electrons. You sort of free up electrons that are held tightly to the nuclei, and they're more readily conducting, and therefore the resistance decreases because we have more readily flow of electrons. So that's an NTC, and I say kind of up here, hey, if you can have an NTC thermistor, you can have a thermistor, right? So you can have a positive temperature coefficient. So, and here's just like two different curves for two different types of thermistors, again, thermal resistors. And you kind of think about, well, what would be the purpose of having this? Why build components that the resistance depends upon their temperature? This is where practical applications sort of, come about, where we can say, hey, it'd be useful to know if the circuit changes due to some change in temperature, we can maybe use this as like a sensor, right? Like if something gets really, really hot and it changes something in the circuit that maybe makes an alarm go off or a light or something like that, like warning, this thing is getting too hot. So you can imagine how, people kind of very clever and come up with, the properties of this thing will change based on if there's light, like there's light dependent resistors, right? If light is incident upon them, then their resistance changes. And so like, when it gets dark outside, the street lights automatically come on. That's because they have these light-dependent resistors in them that can sense, oh, it's not light out anymore, and the resistance in the circuit changes, and it triggers lights to go on. Same thing here. There I remember reading about one of the uses, like a, it would sound an alarm for like SIDS, sudden infant death syndrome. So sometimes babies just, there's no explanation for it. They'll, pass away in their crib and they stop breathing. And if you have one of these thermistors, then the baby's breath sort of keeps it cool. As long as the baby's breathing, then it keeps it cool enough. If it stops breathing, then the thermistor will sort of increase in temperature enough to sound an alarm that, the baby stops breathing. So that's one of the that I recall reading. Diodes, yet another non-ohmic component. So I'm just kind of going through all different sorts of non-ohmic components. Filament lamps, thermistors, now diodes. Okay. A diode, like a light emitting diode, an LED, right? You probably have heard of that before. So a diode is something where we kind of only let charge go through one direction, because again, this certainly isn't a straight line. This is its IV characteristic. It's like basically a flat line, and then at some, what we call threshold voltage, and it's usually around, 0.6 of a volt, depends on the type of diode. Silicon and germanium, they've got their threshold voltages here. Then it starts to decrease. Remember, with a flat slope, that's like infinite resistance. Like it's not going to conduct at these low voltages. As soon as you get close to that threshold voltage, though, it drops from infinity and it gets to, a lower resistance. And that's sort of the point, that once you overcome that threshold voltage, it's going to shine. Okay, the light emitting diode will, light up, or the diode will conduct charge across it. This is the symbol for a diode. Note that the positive is the side with like the arrow, like charge goes from positive to negative. That, remember, is the convention that was adopted before we discovered electrons. We didn't really know that it was the electrons that are going like from positive to negative. We just defined, hey, current, goes in a circle. Now let's make it go from positive to negative, from this kind of charge to that kind of charge. So you can have what's called a reversed biased diode. And that's like if you wired it backwards, then it basically acts as a gatekeeper. It will not allow charge to flow through at all. Like it will only go this way and only when you've overcome the threshold voltage. So it's kind of used as a gatekeeper. Only let charge sort of go in one direction. So forward bias or reverse bias diode, depending on how it's sort of wired there. But you should know this symbol as the symbol for a diode. Let me jump ahead a little bit. All right, so here we have a diode and a lamp. So these two components are in a series circuit. Here's our EMF, and you can see that here's the positive terminal. So this is the direction of conventional current flowing through. And you can see that if the diode is wired this way, then it's got that infinite resistance. And so you see the light. In this one you should. In this one it would not be lighting up because the diode sort of, like I said, acts as a gatekeeper. It's not going to allow any charge to flow through if you wire it up this way. It has to be sort of this arrow pointing in the direction from positive to negative, right, where this is positive. And that's really the sort of the last slide there. This one is a slide that sort of talks about what's called band gap theory. And so metals like copper, their conduction band overlaps with their valence band. It's like the electrons in copper are readily conducting. They're in the conduction band. But depending on the material, they've got valence electrons, but they're not sort of going to conduct. You have to give them an input of energy. And so on the vertical axis here, you can see like energy, and it tells you how many kilojoules per mole of energy these substances need to sort of promote their electrons from the valence band to the conduction band where they will conduct. We saw a few weeks ago that air is a great insulator, and yet you can input enough sort of energy right in the electric field. If you make the electric field strong enough, you can get even air to conduct electricity, right? And so something like diamond, really an insulator, so it's got a high band gap. There's a lot of energy you need to put into diamond to get its electrons to conduct. Silicon, not so much. So like silicon computer chips, germanium, which you can see is also a semi-metal. It's the same sort of number of valence electrons as silicon. It's just a little bit heavier, right? So it's the next one, the next row on the periodic table with the same column. And so the idea is that we can input energy either in the form of thermal energy, like we talked about with thermistors, or maybe light energy, we call it light-dependent resistors. And so some form of energy gives the electrons the energy they need to start conducting. And that's why some things will actually decrease their resistance, at higher temperatures. Or usually, like we saw with the filament lamp, the resistance increases at higher temperatures because the atoms are moving around so much more that the electrons crash into them. But one reason that we could actually lower the resistance with an increase in temperature is if we have this situation, something that's like a semiconductor that needs that energy to kind of free up its electrons. And so there's no simple rule like, oh, when things get hotter, the resistance always goes up. That tends to be true, right, for like metal conductors. But there are certain materials like semiconductors that need that input of energy to overcome this band gap so that they can conduct. And so that, like, if they're conducting more readily, they're less resistant to the flow of charge, right? So the resistance is actually decreasing with inputs of maybe thermal energy, maybe light energy, kind of depends. All right, so that's just a quick run through of some different types of components. We'll certainly see some work examples where these components show